Hello again. My name is Craig Taverner, and I'm going to be presenting building spatial search algorithms for Neo4j. And this is going to be based on a mixture of some old work that we've done, as well as something we did very recently this year. So to start with, I have an agenda where I've tried to minimize the old stuff into just a 2-minute history. We'll see if I can achieve that 2-minute deadline. I'm then going to talk a bit about what's currently available in the standard Neo4j that's shipping today, and then move on to the spatial algorithms themselves. So we've actually done some recent work in an internship where we built some new algorithms, and I'd like to show you how we can demo those in a full stack application. So quite a bit of the presentation I'm going to spend actually going through each of the algorithms and explaining to you how they work, how we wrote them, and how we use them. Let's start with the 2-minute history. So you probably know, if you've seen any of my previous presentations, that I've been involved in Neo4j since 2009, and in 2010, I did a collaborative work. I was a community member at the time, not working for Neo4j. I did a collaborative project with Neo4j to build a GIS modeling library, which we called Neo4j Spatial. This is not something we recommend that you use these days because it was designed for the embedded deployment that Neo4j focused on in those days, and now Neo4j has been a server deployment for many, many years. You can access some of this through the server, but its history shows somewhat. It's also not a spatial database. It's a spatial modeling library. Its strength is only in that because it wraps well-known libraries like JTS and GeoTools, it is very, very comprehensive. But it is not very scalable, and it has issues that you would really experience in an enterprise deployment where you have high concurrency, high volume situations. So only look at this if you are interested in the features and you're not going for a high concurrency, high volume. The one thing I wanted to highlight about it is that at the time in 2010, we also wrote an OpenStreetMap importer and a in-graph OpenStreetMap model, which is something that we still use today and is a major part of the algorithm work that we've done this year. So I'm going to talk about OpenStreetMap more later on, so don't worry too much about the clutter of this diagram. I show it because I have nostalgia for this picture. I drew it in 2010 when we first built OpenStreetMap, and it's a bit archaic, but the model itself is still very similar. The most interesting thing to take away from this is that OpenStreetMap is one single fully connected graph of the planet, and that's fantastic. There's almost nothing in GIS that's like that. So I'll talk about it more later. Just remember that point. The last thing to say about the old library is it's very extensive, but only if you use it in embedded mode, because it wraps all of these other capabilities. The one thing that we did to support it in servers in 2016 was to add some procedures so that you will be able to access some reasonable subset of its capabilities within a server deployment. And that's the last thing to say about the old library, because I think I'm assuming 99% of you are going to work with the new stuff. It's good to know the old one's there in case you need to use some of that. So what is new? Neo4j 3.4 introduced 2 new data types. And this is the first time in a decade that Neo4j had introduced a core data type that was new. The one was the temporal types, of which there were a whole bunch. And there's lots of documentation on that elsewhere, so you can look at that. I'm not going to talk about that today. And then there was the spatial types. We only supported natively in the graph one type, and that's a point, a simple point. But we did make it a little bit powerful in the sense that you can have both 2D and 3D points, and they can both be in geographic and Cartesian coordinate systems. And I'll talk more about geographic and Cartesian throughout this presentation because it's an important factor when it comes to the algorithm development. But for 2D and 3D, this presentation is going to be about 2D only, so ignore 3D for now. Another thing about the native type there is that we developed a spatial index. I have a slide or two on that. But there's only one algorithm built into Neo4j, only one, and it's distance. I say only one, but there are actually two incarnations of it, one for Cartesian, one for geographic. Slightly different calculation, because Cartesian is just Pythagoras, and everyone's written Pythagoras, whereas geographic is a little bit more complicated with trigonometry. And I'll mention that again later. So to describe in brief how the index works, just so you know about it, we targeted a particular use case, which was to find points inside regions. Unfortunately, what's built into Neo4j today only supports the special case of the region being a circle, requiring that you can find points within a distance of a point of interest. So I will describe that now, and then we can show you how you can enhance this to actually support regions, even if Neo4j doesn't do it natively. So if you have a query like the one at the top, where you've got some point of interest, it could be written into the query as I've done there, or pass it in as a parameter, which is what we usually do in an application. And let's say you have a graph that has businesses of a certain category, and they're at certain locations as expressed by the match expression up there. You can have quite complicated queries that actually have predicates both on the category and the location. And Cypher, if there are indexes on both category and location, it will pick the most appropriate index for highest performance and return the results. And the way it does it with the spatial index is it identifies that distance function. If you look at the predicate thereafter, and it says the distance between the location of the business and the point of interest is less than 10 kilometers. That's what it says right there. It can realize that it can interpret this as an index query. And it does that by putting a rectangle, a minimum bounding rectangle about that circle. And it passes that into the index. That will return all the tiles that have points in that part of the rectangle. And then we do a post filter. And in this particular example here, there was 9 candidates filtered down to 5. And you can imagine, even though we do a second pass filter, if you had 9 million points, the index returning 9 is giving you a massive performance advantage. So this works very, very well. We benchmarked this, by the way, and it is performing very well, comparable to other spatial databases. The last thing to say about the built-in support is what I said before about 2D and 3D, but it's the Cartesian and geographic. So some key points about geographic is that the points are on an ellipsoid model of the Earth, and they're in decimal degrees, angles, latitude, longitude. And this also means that the distance function is going to work differently. In Cartesian, you have no units. So whatever the units are of your points will be the units of your distance. In geographic, we assume the points, the locations are in degrees, decimal degrees, and will return distance in meters. So it's very, very strict about what the units mean. Let's get on to an introduction to the spatial algorithms. So one of the motivations I had for giving this talk this year was that in the spring and summer of this year, we had a very interesting internship as a collaboration between Neo4j and Eindhoven University. And they had a student, Stef van der Linde, who came out to Malmö and sat with us for 3 months and did some work on spatial algorithms. And the task that I set him was to develop a few sample complex algorithms. So we didn't go for coverage. We wanted to have a few complex algorithms that could be useful for benchmarking the performance of the algorithms in both Cartesian and geographic systems. And a very interesting element of the work was to have the algorithms run on alternative data models. So you could have a data model that is a polygon in the graph, or you could have a data model that's an array of points. You could have various different data models, and we wanted to see how these algorithms would perform when comparing those. I'm not going to present the results of the benchmarking here. We can take that offline if you want, but some of the conclusions were that some data models were clearly a lot faster than others, and that definitely makes a big difference to the data model that you plan to choose in how you're going to model your data if you intend to write complicated algorithms on it. Another key element for the geographic side is that we wanted this to work on OpenStreetMap data because that is such a valuable data source. So if you remember that really cluttered diagram I showed you a few slides before, Steph has redrawn it symbolically here, which is a lot easier to understand. This is the typical tree structure of how you assemble complex geometries in OpenStreetMap. The bottom row of that tree structure are the nodes, and that word node is not a Neo4j node, that's an OpenStreetMap node. The term means a point, a location. Then if you go 2 rows up to ways chain nodes together into a line segment. So it's a chain of nodes which will represent maybe a piece of a street or a border of a building, or maybe a piece of the outline of an area, of a park, of a province, administrative region, something like that. It turns out, though, that there's an ability in OpenStreetMap to arbitrarily collect things together in progressively more complicated structures, and that's this relation concept at the top. So relation can contain multiple ways, multiple nodes, ways and nodes, other relations, and you can get very complicated data structure. An example would be a polygon with holes that have polygons inside them, and you need to have quite a complicated data structure for that. So Steph modeled a few ways of doing this, and the way that seemed to work best for us, if you take this example on the left, that's a complex multi-polygon. Let's say, for example, that might be a game reserve or a native area or some kind of park that's made of multiple disjoint areas, and some of them have got lakes in them, and some of those lakes have got islands, and you end up with something quite complicated. We modeled it with a tree structure like you see on the right there, where each simple polygon is a single node containing an array of points. Now, Neo4j natively supports both point and arrays of points, just like it supports integer and array of integer and arrays of any of the primitive types. So that's very convenient. It means that we can use the native Neo4j types in order to structure this. So the complexity comes only in the tree structure. And this is working very, very well. And the demo I'm going to show today is based on this data structure. And as you can see, you can have multiple simple polygons containing multiple holes, which can contain multiple simple polygons, which contain multiple holes, etc. It can be arbitrarily deep. And this is possible in most GIS systems as well. But it's very convenient in a graph because we have the var length concept, the traversal of the graph to find these things. And I'll show you examples of that later as well. One important point, though, I mentioned it before, and that is that geographic is a bit different. What Steph found is that there is a whole class of maths for algebra, for the spatial algebra, that uses the n-vector representation. So a point on the surface of the planet is modeled by a vector normal to the surface. Then 2 points, which make a great circle, as you see on the right-hand side there, will be modeled by the vector normal to the great circle, which is what we've shown there. And there's quite a lot of algebra that we've got inside our algorithms that are based on this concept. And I'm going to show you a little bit of that, but try to avoid going into too much detail because it's a bit mathematical, and it's worth reading Steph's paper if you want to know the details. So I have got 6 algorithms to show you. The first 2 actually we demoed last year at Graph Connect and in a few meetups after that. By we, I mean Will Leon and myself. We developed the first demo, and he focused on the root finding and I focused on the point and polygon. So I'm just going to go through that first before I show you a demo of the new stuff. Don't want to go into it in too much detail though. So this is what we showed last year. The simplest root finding you can do, of course, with Cypher is to just use the built-in Cypher shortest path function. This is not the best choice. It tends to give you non-ideal paths in the real world. And Will showed this scary face to show how upset he was about when he first found this bug, this limitation in using shortest path. Instead, what you want to do is when you are traversing a path, you would like to have weighted relationships where the distance, at least the distance, you could use also the time it takes to traverse based on speed limit and other things like that. But in our demo, we used distance, and it gave a much better approximation than shortest path. So how do you do a shortest path including a weighted function? Cypher doesn't have that built in, but Neo4j actually in its embedded API has had that since 2007 or 8, a long time ago. And lucky for us, the APOC library of procedures has exposed that for us. And that gives us access to these two algorithms. That is the Dijkstra algorithm, which considers weights, and so it will always find the shortest path based on weights, but it doesn't go very fast because it's searching in all directions. It starts from one side and just searches in all directions until it finally finds the other node. The A* is a bit cleverer. You give it two functions, one for the weights and the other one for a preferred direction, or what's an additional cost function, which in our case implies a preferred direction. It tends to be much faster. And so we demoed this last year, and we did it in Manhattan, and you could find the shortest path between where you were and the coffee shop that you wanted to go to. And it worked very well. And here's a small animated GIF that Will put together, showing you some of these shortest path calculations, which is, it was quite effective. So the other thing we demoed last year, the part that I focused on, was the point in polygon. And what I did in the demo was I wanted to limit the potential candidate destinations to certain regions. So I pre-calculated in OpenStreetMap model the polygon of Manhattan and Brooklyn and Queens and various areas, and I stored them as simple polygons. So in last year's demo, we could only support simple polygons. Steph's new stuff, by the way, complex polygons, it's a lot richer. I am getting messages that my network is unstable. Send a message in the chat if you can't hear me. Let me have a look at the chat. It's all good, great. Then I will continue. So it's worth looking at last year's presentation if you want to know how we constructed all of those all the polygons and how we prepared everything. I'm not going to go any of that detail now. I'm going to focus just on the point-in polygon function. And I implemented it in a very simple way, and I exposed it with this function here, Amanzi within Polygon. It was branded with my own brand, Amanzi, back then. And that's a library that's now defunct because Steph's project has completely rewritten all of this in a much better way. And I'll show you that later. What did my old library do? This is the point-in polygon algorithm that I implemented. Basically, take a ray in any direction from the point of interest and count how many times it crosses a line segment representing part of the polygon. If the number is odd, you're within the polygon. If it's even, you're not. And this works great. It worked great for the demos, but there are some limitations. It has some issues with geographic. There's some possibilities where you might actually miss an intersection in some extreme cases because of the great circle curvatures. Also, it goes mad if you go near the date line or the poles. So Steph's improved this a lot in the latest version. One other thing I wanted to mention about this is that if I go back to this query, I'm doing both a distance and a point in polygon, and that's because the distance triggers the index and the within polygon does not. So how do you trigger the index for polygons when Neo4j doesn't even know where they are? It's possible to do it with another trick, and that is if you have a second function called bounding box that takes the polygon and builds a rectangle around it, you can then use the query. If you look at the third last line there, find the location that is greater than this bottom left corner and smaller than that top right corner. If you say that, if you write that to Cypher, it will figure out that you want to use an index, and it will use an index. So that's a good trick where you can actually trick Cypher into using an index for a case where you wouldn't think it's actually capable. And this is something that's worth doing when you have large amounts of data. So before moving on to the actual the next set of 4 algorithms that Steph implemented, I'm going to switch to a live demo. Let's find that window. Let's see, is the demo appearing yet? It looks like it might have appeared. Right, I think I can see it. So this demo is the same application we used last year. It has the routing and all the rest. I'm not going to demo that part. That's down here in Malmö. I put this pin at the Neo4j engineering office. Instead, I want to show you the new stuff. And the new stuff involves the fact that we've built these polygons according to that tree structure that I showed you that Steph made, where we can select on the left here. I can select the polygon representing Skåne. That's the province that we have our office in. And you'll notice that the OpenStreetMap view of that province actually includes part of the sea, because it's part of the administrative region. You can, of course, perform intersection calculations, and I've done that in advance to show you the intersection between the province of Skåne and the land area, and that uses the intersection calculation. We can also click on the map now. There's a little demo I made to click here. I clicked and I get the administrative region around Stockholm. And this uses the point in polygon function, the new version, to give the polygon over there. You can click pretty much anywhere and take them away, for example. You can also show areas. So this is actually, when I click that, it actually goes to the database and says, give me the area of the polygon. And that actually involves a traversal of the database, finding those things, calculating area and returning it to the client. And as you can see, that was very, very fast as well, which is very nice. The next part of the demo is not so fast. I'm going to say debug distances down here and ask it to calculate the distances. And that took a little while, so I'm going to make it take even longer. I'm going to click on another polygon, and this is going to take quite some time. So while it's busy doing that, I'm going to explain why it's so slow. The actual calculation between 2 points is very, very, very fast. The problem is finding which 2 points of the polygon are closest together. And at the moment, we have an algorithm that is just brute force. It's breaking up each of the polygons into little line segments and looking at all combinations. So if you just compare Skåne to Stockholm, it's going to, let's say Skåne is 1,000 line segments and Stockholm's another 1,000. It's going to look at 1 million possible combinations, calculate all those distances and find the shortest before it's going to return something. And if you have 3 polygons, it's going to do that 3 times if you look at all the combinations. It turns out that this one's even slower than that because of something surprising, which you should see in another 10, 20 seconds when the results come in. And that is this particular one. Yeah, there we go. Took its time. You would have expected 1 line between each of these provinces, but look at this weird line in the middle here. When I first saw that, I thought, I have a bug in my calculation. It's not a bug. It's a result of the way I queried the database, and I'll show you the Cypher query in the slides. Look down at this area there. It turns out this polygon has a hole. For some reason, the people living in this area wanted to be in the province adjacent to this area. They didn't want to be in that province. So this is a hole and actually belongs to the other province. So when I searched for my simple polygons to calculate distance, I actually search for shells and holes. And as a result, I'm finding the distances between 4 simple polygons here. The last thing, I'm going to take that away. The last thing to show is convex hull. So that was very quick. I hope the screen refreshed. I'm going to take it away again, put it back. You'll see that it's very quick to calculate convex hulls. This was actually calculated live. I'm going to select a bunch of provinces, and you'll see that convex hulls overlap. If I take away the convex hull, the provinces don't. So you might already have guessed what a convex hull is. Let's go back to the slides, and I will explain in more detail. Let's find my slides. They should be loading now, I think. Great. Let's go, there we go. So now we're going to go through the 4 algorithms that I've just demonstrated: the calculation of areas, intersections, distances, and last but not least, convex hulls. So how do we calculate areas? That top equation might look a little scary, but it's not. The important points to notice is that you divide the area by half. I'll explain why in a second. Then you sum over this xy. Xy is basically the cross product of 2 vectors. And we subtract a different set of xy's. So to explain how that all works, look at the diagram. What you can do to do this shoelace formula is choose an arbitrary origin. It doesn't matter where. It can be inside or outside the polygon. In this case, we have it outside. Now you take each line segment that builds up the polygon, and a line segment is made of 2 points. Calculate the triangle of those 2 points back to the origin. And the area of that triangle is the cross product of the vectors, which gives you the area of a parallelogram. You divide it by 2, you get the area of the triangle. So the divide by 2 there is coming from the conversion of the area of the parallelogram to the triangle. All of the green triangles are the ones on the left. They are too large an area. You need to subtract these other orange ones. So we need to know when we're going around which side of the polygon we are. It actually works out naturally from the cross product whether you're going to get a positive or negative value anyway. So you take all of the green and you subtract all the orange, and bang, you have the area. So the shoelace formula is actually very fast and efficient. But this doesn't really work in geographic coordinates properly. There's some conceptual similarities, but in geographic one, we do something that's somewhat more complicated that involves calculating great circles. And there's another theorem called Girard's theorem that produces the area as an equation from the great circles. I will show you briefly the code for this, but I'm not going to go into detail. It's a little bit complicated. It's better to read the paper. So how do we query that? Well, this top line in the match you might have seen before. We find the relation. That's the top of the relation, and you var length traverse down this tree structure that I'll show you on the right to all of the subpolygons that are within that relation. And I do this for every single relation in my set of relation IDs. So if I'm calculating the area for 20 polygons, then that will have 20 region IDs over there. And the most important thing is the very last line, return spatial.algo.area. This function is taking the simple polygon represented by that property of that node, passing it into the function, returning the area. And as you saw in the demo, super fast, which is really nice. So while we're showing you one algorithm, I'm actually just going to switch quickly to the code for that. Let's see if I can find that. Let's see when this appears. How do you actually write code that can be accessed from Cypher like that? We've got other presentations on this. I'm going to be very brief about it, but here is a simple set of 3 user functions. We use this annotation. If you're not a developer, ignore the next half a minute of my talk. Otherwise, maybe this is interesting to you. This is the name that we refer to it in Cypher. And then we pass it in the simple polygon as a list of native Neo4j points. We're going to convert it into the data structure that we've used in our library as a simple polygon. This get calculator just says, give me a calculator for Cartesian or geographic. It has a look at the data and then deduces that for you. So we can now go to the implementation of the actual function. It's abstract because we have two different versions, Cartesian and geographic. So let's go to geographic. It's more complex, but it's not that bad. It takes only one page to do Girard's theorem. It's, as we said before, you've got to traverse to find all of the traverse the data to find all the great circles, and then you do this angular calculation that was in the equation that's used by Girard's theorem, and it works really, really well. The other functions, we have spatial distance and we have spatial distance ends. The difference between these two is only that in the spatial distance ends, I'm actually going to return the distance as well as 2 points representing which 2 points were closest between the two polygons so that I can show it in the demo. So this function I wrote just for the purpose of that demo. I'm not going to go into the actual code for that. I don't want to spend much time on code. I'd like to go back to the presentation. Let's see, that should take a second to come back. See how we are for time. All right, looks like we've got 10 minutes. I better be quick. Let's not spend too much time on these other ones so that we have time for questions as well. Intersection, it's a little bit complicated, so I'll try to be brief. We've got this concept of a monotone chain sweep line. You can Google for that if you want more, or read Steph's report. But basically, you break all the geometries down into pieces of line segments that don't ever overlap, don't fold back on themselves on the x-axis. So you end up with this, and then you sweep across it. And you can, as you sweep, by reordering the points, you can detect intersections. And that's what happened in B over here. And every intersection is just added to a stack, and you continue the sweep. And at the end, if you have no intersections, they don't intersect. If you have intersections, you can actually produce an intersection geometry. In geographic coordinate systems, we needed to consider the fact that any 2 points don't define only one possible line, they define a great circle. So we could mean the other side. Which side do we mean? We've had to have some rules for deciding how that works. We don't, I mean, if you look at the intersections here, the red is defined by 2 red points, the blue by 2 blue, but which do we want? We want the black intersection or the gray intersection? We want the black one in this case, and we need a rules for defining that. Another consideration for geographic is if the polygon touches or overlaps a pole, things go haywire. So we have to have some detection code for that. And it turns out that if you simply traverse around the polygon calculating the bearings and summing them all up, you will end up with 360 degrees if you don't touch or overlap a pole. You will end up with plus or minus 360 degrees depending on whether the polygon is anti-clockwise or clockwise, which is very important. Many GIS systems will use the direction to define whether it's a shell or a hole. So it's quite important to know that. It also affects our area calculation, the green or the orange that we talked about before. So this is a very important thing. We, in our current maths here, we're not actually calculating areas and intersections. If they do intersect the poles, we're just throwing an error because you have to change to a totally different algorithm. And we assume that that's an edge case. If you want to add to the library and code for the poles, you're welcome to do it. The next one is distance. And the reason I did distance after intersection is only that the first thing the distance calculation must do is work out if they intersect and return 0. So we had to code intersection first. So distance, it did the stuff I told you about, that doubly nested loop to consider all combinations, and then finally it gets down to deep down, what is the distance between 2 points? And so what I'm showing here is the version of that for geographic coordinates, which is a cross product again, and the arctan converting it back into distance on the arc. So it's a pretty straightforward equation, and it's very, very efficient and very, very quick. That part's quick. As you noticed, that doubly nested loop was not quick. How do we query this? I'm trying to show you cipher examples for every one, and this is unfortunately the most complex cipher. The part you probably care about the most is the very last line. Very simple, spatial algo distance ends, if you want those points, pass in two simple polygons. All the rest of that cipher is just finding all the polygons for those provinces, making sure that we get the polygons as these things, and then we can pass it into the equation there. But that's pretty standard cipher. What you might notice is that I've got this concept of pairs, so I am passing into the query all combinations of provinces up front, and I'm doing that in the application and defined by just an integer ID, so we can do a quick search. So the first part of this query is very fast. The only part that's expensive is that finding closest points. So I'd love to find a way to optimize that. The last thing to show before we have hopefully a few minutes for questions is the convex hull. You might have deduced what convex hull means by looking at this. If you haven't, I'm going to explain it. It's not too bad. If you compare those two, the first thing you can see is that the right-hand side looks much simpler, but the word convex means it doesn't have any dents in it. It only has rounded surfaces. A dent is called concave. So the polygons on the left have got lots of little dents. They've got convex and concave shapes to them. Convex hull is like taking an elastic band around that shape, and the elastic is not going to dent in. It also simplifies the polygon dramatically. The way we calculate this is, the first thing you can say is that convex hull doesn't require polygons. It can work with any kinds of geometries. You can have a complicated line segment, a highway or something, and you do a convex hull around it. It'll be the elastic band around all the points of that line segment. So the first thing you do is just turn it into a bag of points. And then what we do is pick an origin. Normally, by convention, you pick the southernmost, and if there's multiple ones at the same south latitude, you're going to take the westernmost of those, the most negative or smallest x value. And you make that the origin. Sort all other points in anti-clockwise order by angle, and then you just start sweeping through it. And this version is the Cartesian version. I'll show you the geographic version in a second. It's only slightly different. When comparing any three consecutive points, in this case A, B, and C, we calculate the angle from A to B versus B to C, well, the angle at B. If it's less than 180 degrees, B is a concave piece, and we throw it away. So all this algorithm does is throw away, step by step, all points that create anything concave. So it's reducing the total number of points dramatically. And it will then go AC to the next one and do the angle there. So it's going to sweep all the way around and throw away all the concave points. So why does this not work in geographic coordinates? It's to do with that angle and the lines, because the calculation of the angle on a curved surface is a problem. What we really want to know is, if you imagine a straight line between A and C, is B to the left or the right of that line? And another way of asking that question is, the vector from origin to B, does it intersect? Does that line segment, origin to B, intersect the line segment AC? An intersection we've already solved for geographic. So that's what we do over here. Here is the calculation. And you notice that if you look at that red line, the line of constant latitude is a gray curve below the red line. So we have to be aware of geographic coordinates, otherwise we're going to get it wrong. The actual line we care about is the great circle, which is the red line. So we need to work out an intersection of the great circles. That's the important part, and we've got that solved in other places. And that gives us the convex hull in geographic coordinates. And this is how we query it. Those two pictures were queried with identical queries, except that very last line. You see, instead of just returning the polygon, we return the convex hull of the polygon super fast. It's doing the calculation every time I click that button. It was very, very quick. Very, very nice. So this brings us to the end. It's almost the end. We've got some Hunger Games questions for you if you're interested. I will leave this up on the screen. I have some references as well. You can get that from the presentation later. We don't need to look at them now. Instead, I'll leave Hunger Games questions on the screen. And see, we have a few minutes for questions and answers. So there is a Q&A section over here. I can see some questions. Let's see. Okay. The first question, I'm wondering if it is possible to draw, for example, 15-minute drive time area in Neo4j. Okay, one of the algorithms that Steph actually implemented is a thing called linear referencing. And linear referencing is to take a geometry, which is, it could be a polygon or a long line segment, and say, give me the point that is X meters along this geometry, if you've defined how to calculate meters. And so that's what we've done. I didn't include it in the demo, but it's definitely will answer your question. You've asked for time. So the calculation we did was based on distance, but it wouldn't be a big issue to change the way you do that. But you need to then, of course, model speed limit or something, because the GIS data will include actual distance. And if you put speed limits on that and model your speed, then you can also do the same equation in time. So yes, it's possible. Then we see Max Damazi asks, if you have drive time as weights in the relationships, you could do this by first getting a circle of points at the max speed, let's say, and then for each point calculate the shortest weighted path back to the origin within 15 minutes. Is that a circle of points as the crow flies? Because I think that if you talk about routing across a graph, it's never going to end up being a circle, right? Unless you use the circle in order to trim the result set down into the minimum possible search results. Yeah, that sounds like a good one, because then you'll get it indexed back. Sounds like a good idea. Ivan asks, where can I download a copy of the slides? I believe all of these presentations are going to be shared with all attendees later. I know that I've made the presentation links available to the organizers, so I think they will provide that to you afterwards. Maurice asks, how many points or polygons will still be scalable? Example, find Tesla superchargers in the entire Europe or Amsterdam to Cape Town routes. Well, first of all, there's no superchargers in all of Africa, I'm sad to say, which surprised me. But yeah, in principle, this should scale very, very well. I mean, Neo4j can handle many, many billions of nodes. But as you've seen, that every algorithm, depending on the algorithm, can have performance issues. The distance algorithm we had there with only 1 million combinations was showing problems. I'm sure it's possible to improve the performance of that. But it's always a cost-benefit ratio. One thing I can say, what we did discover, I mentioned this in the beginning when we modeled polygons as raw OpenStreetMap graphs versus arrays of points cached in a different graph structure, that we got a massive performance improvement. So that kind of thinking can be taken further. Every time you have a performance problem, what you want to do is find out where is the cost, and the cost can be both in the way you're iterating too many times, or it could be in the data model. In this case, it was obviously improved by data model. So you can improve your data model in a way that will improve your performance, or you can improve the algorithm. I think that I would be surprised if there's anything that can't be solved here in terms of scalability. And Tesla superchargers, there's only 50,000 of them. We're not going to have a problem. That's a very small number. It should be very, very quick. Okay, that's all of the questions that I have over here. I'm sure that you people will be leaving to go to the next session. I'll stay online a bit longer if anyone else wants to ask anything, but you're welcome to attend the next session.